So at the end of this lesson, you will be able to solve the roots of polynomials system and also the system of non-linear equation. This is our objective for this class today, solving for polynomials and also non-linear equation. So multiple roots, this is the things it's happening correspond where to the points where the function it's touching the x-axis at one point. Okay, just only to recall back is what we have done for the last 2 weeks. We were talking about finding the roots of the equation. You need to find the value of x. So let's say that you are having a function x, function of x. So you need to find what's the value of x that it's going to make the function will be equal to the value of 0. So this is what we were looking for. Okay, so you need to find this value of x. How actually we found that value of x? We are having a bracketing methods and we are having the open methods. So we are having bisection method as a bracketing method, false position methods as a bracketing method, and we are having fixed point iteration as an open method, Newton-Raphson and the second methods as an open method. So all these methods, they are working is to find this value of x to make the function is equal to 0. But actually what was happening here, let's say that you are having this figure in here. So this is the x-axis. And this is the y-axis, or this is called the function. What we were looking for when the function, when you are drawing it, when it's crossing the x-axis, so at this place here, at this position, this is considered is the root, because here it's x, it's equal to 0. So it's easy to use bisection method, false position, Newton-Raphson. You can use the second method, and also you can use the fixed point iterations to find this point. But here for the multiple root, what's happening here, it's in somehow a little bit different. So what you're going to get is, this is correspond to the point where the function is tangent to the x-axis. So what's happening here today, so let's say we are having this figure here. This is the x-axis. This is y, or the function. What happened here is, when you're going to draw the function is going to be coming to x-axis, but it's not going to be changed the sign. It's going to be just only touch the x-axis at one point and go up again. So it's here. So that's why you say here it's correspond to the point where the function is tangent to the x-axis. So in that case, if the function is touching the x-axis, remember it's when we were saying about the bracketing methods and open methods, the functions have to change the sign. The function has to go, like, let's say, from positive sign to a negative sign. So it's easy, you can use any bracketing method. You can use a bisection method, you can use the false position, or you can use the second method, or you can use the Newton-Raphson. But in this case in here, the function, it doesn't change the sign. So the function here came from positive, touch the x-axis, and also back to positive. So it's not changing the sign. So in this case in here, if you try to use bracketing methods or open methods, you are not going to get this answer. You are not going to get this value. So this is considered a limitation of bracketing methods and also bracketing of limitation. This is considered a limitation of a bracketing method and also open method. Okay, so sometimes if you are going to use it for the polynomial, let's say we are taking this function as a polynomial, we can see that there's two terms of this polynomial, which x's can make the terms to be equal to 0. That's why we call this one is a multiple root. And in this case of triple roots, there will be one value of x that makes these three terms of the equations equal to the value of 0. So this is considered it's a multiple root. So what we are talking here about is if you are talking about the multiple roots, this is poses several limitations for the numerical methods that we had learned before. When we are looking at this figure in here, the value here came from negative sign, touch the x-axis at this point, and back to negative sign. And here coming from the negative sign, and here it's changed to a positive sign. So when we are looking at this function has double roots, which is the value of 1 and the value of 3. But if we are going to use bisection methods, false position, or fixed point, Newton-Raphson, or the second methods, we are going to only find the value of 3, because this is the value is change the sign between negative to positive. But you are not going to find this value. That's why it's considered here is a serious limitation or several limitations of most of the numerical methods that we had learned past 2 weeks. Okay, it could be also happen that you're going to have a triple root or the quadruple roots, so it depends on. But now let's see if you are going to have the function with the even multiple roots. So the function doesn't change the sign over the interval. So this is considered it's not reliable to use it for the bracketing methods. So you cannot use the bracketing methods to find this answer here. You will just only going to find the value of 3. If you are also in the case of the multiple roots, the function itself and the first derivative of the function will be equal to 0 or approaching 0. If the function or the first derivative of the function is equal to 0, this is going to be a serious limitation of using the open methods of Newton-Raphson, and also for the second methods. If you remember, it's the equation of the Newton-Raphson. It's equal to to find the new value of x, it's equal to x minus the function over the first derivative of the function. So if the first derivative of the function is 0, you're going to get an error, which is division by 0. So that's why here in a multiple root, the first derivative of the function or the function itself, it's almost 0 or approaching 0. So this is considered its serious limitations of the Newton-Raphson. So how actually we can overcome these two problems when we are going to have a multiple roots? We can use something we call it here, it's the modified Newton-Raphson methods. So we are going to modify the Newton-Raphson methods that we had learned last week, and we are going to use it to find the multiple roots. So that means we are going to find this value, and also you can find this value. Okay, so even though this value here is just only touching the x-axis, it's not crossing the x-axis. So how we can do that? Using the modified Newton-Raphson. So how actually we can find the modified Newton-Raphson equation? Again, I'm repeating, you're not going to be asked to derive the equation. The equation is going to be given. You're just only going to use. So how to get the equations? We are introducing a new function. We call it ux as a ratio of the function and its first derivative. So ux is equal to the function over the first derivative of the functions. So this function here, if you are going to find the derivative for it, so you are going to get this equation here. Okay, so by combining, putting this one, it's ux and the first derivative of ux inside the equation of the Newton-Raphson, you are going to get the modified Newton-Raphson equation. So to predict a new value of x is going to be equal to x minus the function times the first derivative of the function over the first derivative of the function square minus the function times the second derivative of the function. So here you need to find the first derivative of the function, and also you need to get the second derivative of the function. Why we are going to get that one? So when we are going to get it, it's the denominator will not be even equal to 0, even if the function itself is equal to 0. So it's going to be more stable. So the equation is going to be more stable. But actually, we are not preferable to use it for the multiple roots because somehow it's less efficient, and it's seldom to use in practice because more computational efforts involved. because you need to find the first derivative. Also, you need to find the second derivative. So it's seldom to use the modified Newton-Raphson equation. Okay, let's see how we can solve this modified Newton-Raphson using this example in here. We are having this polynomial x cubed minus 5x squared plus 7x minus 3 with the initial value of x is equal to 0. This example is asking you to use both standard and modified Newton-Raphson. We are not going to use the standard Newton-Raphson. We are going to just only use the modified Newton-Raphson because the standard we already had learned it last week. So we are going to use the modified Newton-Raphson. So we are going to use this equation here to solve, to find the root or the multiple roots of this function here. With our initial value of x, it's equal to 0. This example in the textbook at 6.9. Okay, so since we already had learned about Newton-Raphson last week, so I'm not going to do the example with you. I'm going to give you a time about like 10 minutes or 15 minutes, just only to try to get those value here. So let me show you the example. Just solve it for the modified Newton-Raphson. Okay, let me share with you the Excel file. Okay, if we are going to solve this one using the standard Newton-Raphson, this is what we had learned last week. So we are going to do that. Actually, it's the true value for that function. It's supposed to be equal to 1. But now what I want you to do is repeat. You repeat this example to solve for the modified Newton-Raphson. So this is the equation of the modified Newton-Raphson. Remember that you need to find the first derivative and the second derivative of this function here, and you start with the initial value of x, it's equal to 0. So your second value, you're supposed to get the answer of 1.105, and for the second iteration, 1.0, and for the third iterations, you are going to get the true value, which is equal to 1. If you substitute the value of 1 in here, this function will be equal to the value of 0. I want you to try that. I'll give you about like 10 minutes to try it. If you have any questions, please ask.
So,
Yes.
so it means that every time we going to use modified Newton-Raphson, the SI for the 0 iteration is going to be 0.
No, the initial values is going to be given in the question itself. So maybe sometimes you're going to start with the value of 0.5 or 1 or sometimes 5. So it depends on the question. This example here is asking you to start as an iteration or your initial value x is equal to 0. So we start with the value of 0, this one.
In the exam, they will give this formula or we have to memorize it?
No, don't memorize anything. All the equation is going to be given in the appendix.
All right, thank you.
Thank you. Did you manage to get some values?
Yes, sir.
Is it clear? Okay, so now let's move to the back. Let me change the screen. Okay, this example, you can find it also at the textbook 6.9. Okay, this is the exercise. Use the modified Newton-Raphson method to find the root of the following polynomial function until the relative error is less than 0.05. Okay, first time you can use the initial value of x is equal to 0 and x is equal to. So this exercise, you can try it, and the answer is at the next slide. So you can find the answer is here. Okay, so you can find that it's this polynomial here. It has two values that can make the function will be equal to 0. Okay, so it's the value of 4. The value of 4, this is the value that if you substitute here for all the x's, that you're going to get the answer here is equal to the value of 0. So when you're going to start with the initial value of x is equal to, you are going to find that answer here. Okay, so you can try this exercise by yourself and you can compare your answer with the next slides in here. So now let's talk about a system of nonlinear equations and how to solve the system of nonlinear equation. We are not going to learn about any new methods. We are going to use the methods that we had learned before. So we are going to use the fixed point iteration and also Newton-Raphson method to help us to solve for the nonlinear equations. So before we start, it's there is the linear equations is a function with the values of x, and it could be or having about like having one function or two function or n number of function, which is all this number of functions can be solved as a function of x with the constant value of a and coefficient of x1, a2, and x2 will be equal to the value of 0. Of course, you're going to have a constant value of b in here. But this is not our concern here. What we need to talk about here today is about nonlinear equations. So when you're talking about linear equation, you're just only going to have an x value, which is this is going to be unknown. But when we are talking about nonlinear equation, you're going to have two unknowns that you need to find. So a nonlinear equation, you're going to have x, and also you're going to have a value of y. So here it's what you need to find. What's the value of x and y when you are going to substitute into these two equations? You're going to find the value is equal to 0. So when you are going to solve nonlinear equations to find the value of x and y, you cannot work with each equation individually by itself. So you cannot just simply take the first equation, solve it by itself first, then after you finish, you're going to start with the second equation, then you're going to solve it by itself to find what's the value of y and what's the value of x. You have to solve both of these two equations at the same time simultaneously. Okay, so to solve for the nonlinear equations, you need to solve both of them together. So you can name the first equation, it's u for x and y, it's equal to 0. And the second equations converted to the function of x and y. So I rearranged it to be having is equal to the value of 0. So what's the type of methods that we are going to use to help us to solve for these nonlinear equations to find what's the value of x and y? We are going to use two methods. The first one is the fixed point iteration and also Newton-Raphson. So can someone tell me for the fixed point iteration what I need to do to solve fixed point iteration? We had learned this one last week. What's this methods and what I need to do? Fixed point iteration. What is this method and what I need to do?
Is it for position and bisection method?
Can you repeat again?
Is it bisection method and for position method?
No, fixed point iteration, it's a method by itself, but what's the method, what I need to do?
Rearrange the function.
Fixed point iteration, it's open method. Yes. So I need to rearrange the function to have x on the left side of the equation, right? But in my case in here, when we are looking at this case with the nonlinear equation, I have two unknowns, which is x and y. So in that case, for the nonlinear equation or simultaneously linear algebraic equation, I maybe rearrange the first equations to have x on the left side of the equation. So I will have here x. And for the second equation, I will rearrange it for y. So y is going to be on the left side of the equation. So this is the fixed point iterations using nonlinear equation. So we are going to rearrange the equation so to have x on the left side and y on the left side. Okay, so in my case in here, this is the coming example for the fixed point iteration. Since it's not a new methods, we're going directly to go for the example. And this example in your textbook 6.10. So I have two functions here, and I have two initial values is given in the example. X initial is equal to 1.5 and y is equal to 3.2. By the way, it's the true value that we want to achieve. We're supposed to get the value of x, the true value that to make these two functions equal to 0, that x is equal to, it's supposed to be x is equal to, and supposed to be y is equal to 3. This is the value that we want to achieve, or this is the true value. Okay, but now because we don't know, our initial value of x is equal to 1.5 and y is equal to 3.5. So now we want to use the fixed point iteration. So what we are going to do here, first one, we are going to try to rearrange. So we are going to rearrange based on this x, and we are going to rearrange the second function based on this y. Okay, so we'll put this x on the left side, and we are going to put y on the left side. Is it clear? Do you have any questions how it works? Any question?
Yes.
Okay, so let's see. Let me share with you the Excel file, and please, I want you, all of you, to have a piece of paper and pen and your calculator beside you, because I want you to do the calculations. Remember, we are learning from our mistake. Okay, let me share the Excel file. Share. Okay. Okay, so we are having the functions in here. The first function I'm going to rearrange based on this x, and the second function I was going to arrange it for this y. So when I'm going to rearrange the first function for this x, I am going to get this value here is x is equal to 10 minus x squared over y. The second function, when I'm going to arrange putting y on the left side, so it's going to be y is equal to 57 minus 3xy squared. Okay, so everyone is ready? You have a pen, piece of paper, the calculator with you? Ready?
Yes.
Okay, so now remember, our initial value of x is given in the question or the example. X is equal to 1.5 and y is equal to 3.5. So 1.5 and 3.5. This is our initial value given. And remember that is we are saying that it's fixed point iteration. It's based on open methods. It could be converge and it could be diverge. How you're going to know that is from the arrow. Okay, so now the first value of x is 1.5 and the second value of y is equal to 3.5. So this means my next value of x prediction here, what's it going to be? So I'm going to use the initial values inside the first equation, x here. So x is equal to 1. 10 minus the value of x, which is given here, it's 1.5, over y, 3.5. What's the answer is going to be? 10 minus 1.5 over 3.5. So this means x is going to be equal to the value of 2.21429. Right? You are using the initial values inside this equation here. So you're supposed to get the answer of 2.21429. Okay, did you get the value?
Yes.
Okay, try by yourself to find the answer of y and tell me what's your answer. So what's the value of y here? You can also write in the chat box if you don't have a mic. So someone say it's 1.875. How about the rest? All of you okay with that value?
Yes.
Okay. So the answer is negative 24.375. You're supposed to get the answer of negative 24.375. Okay. Why this one is came and how? Remember, I said it's we learn from our mistakes. Okay, remember what I said when we are talking about the non-linear equations? You need to solve both of the equation at the same time. So this means now where I'm having two equations, x and y, I have to solve both of these two equations at the same time. So now, what happened here? At this first iteration here, I solved the first equation. I get the value of x, it's equal to 2.21429. So this means now the value of x no more is equal to 1.5. The value of x now is equal to 2.2149. So this means now when I go to find a new value of y, I'm not going to use 1.5. I'm going to use the new value. So what's the rule here? Whenever you are having a new value in your hand, forget the old one, use the new value. So now to find the new value of y is going to be 57 minus 3 times 2.21429 times the value of y, which is 3.5 squared. So you'll get the answer. It's negative 24.375. Try. Did you get the negative 24?
Yes.
Okay. Now, to clear up the point and what's happening, because remember I said that it's fixed point iteration is considered as an open method. It could be converge and it could be diverge. How I can know that? Could you please calculate the value of the error for x and for y for these two iterations here? I want you to calculate the approximate error here. So what's the answer that you're going to get? Calculate the approximate error for x and the approximate error for y. How to calculate the approximate error? A new value of x minus the old value of x over the new value of x. Same goes to the y. A new value of y minus the old value of y over the new value of y, you are going to get the error. So you're supposed to have these two values of error. Okay? Now, by yourself, I want you to find what's the answer of X and Y for the new iteration, and also calculate the error. I want you to get these 4 values here. And you can write your answer on the chat box if you don't have mine. What's the value of new X and what's the value of new Y and the error for X and Y? You can write your answer in the chat box. So what's the value of X? And Y? Okay, so X is negative 0.209 and the value of Y is equal to 429. Okay, great. So when you are looking at that now, if you are going to calculate the error for this iteration, so this is the new value minus the old value over the new value, you are going to find the error. Now you can see the error, it starts to increase. It's 1,158, 105, And when you are looking at the values looks very weird. You start from 1.5 at x, and secondly, for the first iteration, you get the answer, it's 2.21. Then suddenly is the value is jumped to a negative value. And when you are looking at the column y, you start with the value of 3.5, then suddenly is a negative value 24, and suddenly it's 429. When you are looking at those values, looks weird, and also the error is start to be increased. So you need to stop. So this means this way of when you rearrange the equations, this is the way of diverge. You are not going to find the root. Remember, our true value we need to achieve here, it's x is equal to and y is equal to 3. This is the value that if you put it inside the equations, the answer is going to be equal to a 0. But now the numbers is too far from 2 and too far from 3. So that's why this way of rearrangement is not going to be converged. So what you need to do, remember last class we said, to guarantee that this fixed point is going to be converged, maybe you need to choose different x to be rearranged. So that means you stop and consider, instead of I'm going to use this value of x to rearrange, I'm going to use the x square. And instead of I'm going to use this value of y, I'm going to use the y squared to rearrange. So maybe my rearrangement is going to be something like this. So x is equal to, root in here is 10 minus xy, and y is equal to the root in here 5, 7 minus y over 3x. And I'm going to start again with the initial values of 1.5 and 3.5. So now I want you to do this example again as an exercise using this two arrangement in here. So you're not using this, you are using these two arrangement, and see what's the answer it's going to be for the value of x and y. And don't forget to calculate the error. I will give you a time. I'll give you about like 10 minutes to solve and check your answer. Do you have any questions what I have done right now? Is it clear what I'm saying? Okay, please try the example again using the new arrangement. I'll give you about 10 minutes to solve, and you can write your answer at the chat box in the Google Meet. Try to solve it full, the 3 iteration, and compare the answer and check if this one is converge or this one is diverge. I will give you the time. Okay, so did you get the answer? You can write in the chat box what's the sequence of the value of x. This is first iteration, yes, 2.17. And second value, 1.9. Good. And 2.8. It's not going to be 2.8. It's going to be 2.0. Okay. And this is the value you are going to get for the value of y. And when you calculate the error, this is the errors. Okay. So now remember that we are supposed to be approaching the value of x is equal to and y is equal to 3 to get the answer. So now when we are looking here, it's at x, start from 1.5, 2.1, 1.9, and 2. So it's closer to the value of 2. And y, it's from 3.5, 2.8, 3.0, 2.9. So it's end up. And when you are looking at the error, you are going to find is the error is decreasing. So this means this way of arrangement of the equations, this is the way it's going to be converged towards the root. Okay? So I think it's clear now. Do you have any questions about it, about this method? Is it clear?
Clear, doctor.
Okay, let's back to the PowerPoint. So the last thing for today. Okay, Newton-Raphson methods. Okay, even though you are not going to get any question coming out from Newton-Raphson methods for the nonlinear equation. So this means you are not going to have any questions at the assignment or midterm or finals coming from Newton-Raphson methods for the nonlinear equations. So this means Newton-Raphson methods with two functions. You're not going to have a question, but I have to explain to you how it works. Okay, so just only for general information here. So this methods here, it's based on the Taylor series expansion for a function of more than one variable. So this means this is how to solve it when you are going to have a function with x and y. So you're going to have two functions and two variables for x and y. So this is for x and this is for y. So the root of the equation is going to be okay when the value of x and y, where it's going to be having the function of u and v will be equal to 0. So this function of u at the end will be equal to 0. And this, the second function of v will be equal to the value of 0. So we need to find the value of x and also the value of y. Okay, so the good things about rearrangement of these equations in here, you are going to get the equation of Newton-Raphson to predict a new value of x and to predict the new value of y. Okay, this is same like fixed point. We are trying to find x plus 1 and y plus 1. So this is the equation we are going to use to find x. This is the equations to find y. So it is going to be equal to the initial value of x and the initial value of y. The good things about these two equations in here, even though there looks a lot of calculation in here, is the determinant is based on the Jacobian system. So they are equal to each other for the determinant. This one is equal to this. So when you calculate it one time, it's considered you calculated for x and y. And it's based on the partial derivative of the function. Okay, so if we are going to follow the same example that we have solved using the fixed point, we're supposed to get the answer of x, it's equal to, and also the value of y is equal to 3. So here when we are going to solve, since we are not using fixed point, we are using the function itself to solve, but based on the partial derivative equations. So how it works, let me show you the Excel file first. And by the way, this example also in the textbook, you can review it in the textbook, but I will explain it here in the Excel. Okay, it's 6.11. Okay, so this is the example. X squared plus xy minus 10 is equal to 0. Y plus 3xy squared minus 57 is equal to 0. And this is the equation how to find the new value of x and the equation to find the new value of y. So what we need to do, we need to find all these terms of the partial derivative of the function for v over y minus the v values. Okay, so how to do that? First, we need to find all these terms. So how to find those terms? We are taking the first function here, which is the function u. So one function u for x and y, we need first of all to find the partial derivative for these functions based on the x. So if you partial derivative this function for x, what you're going to get? This is x, so it's going to be 2x plus x, here is partial derivative, so it's going to be y. So this means it's going to be 2x plus y. Okay, what's the initial value it's giving to us? The initial value x is equal to 1.5 and y is equal to 3.5. So 2x, this means 2 times 1.5 plus y is 3.5. So the answer is 6.5. So now these terms in here, you are going to try to put the value here at this position. 6.5 is going to be here. Okay. So now again, the first function, you are going to find the partial derivative for the value of y. So there is no y at this term. There is y at this term. So this means it's going to be equal to x. So x is equal to, initial value is 1.5. So try to find this at here. So this one is going to be u and y is going to be here 1.5, and here is going to be 1.5. Okay. Then look at the second function here. We are going to make it a partial derivative for x and y. Let's start with x. So there is no x in here, so we are not going to do anything. There is an x here, so partial derivative, so it's going to be 3y squared. Use the initial value, 3 times 3.5 squared, so the answer is 36.75. Find the partial derivative for the second function for y, so it's going to be here, y is 1, plus 6xy minus 57, so you are going to get the answer here is 32.5. So now you have all these values. The initial value of x, 1.5, you put it here. The initial value of y, you put it here. And the value of u and the value of v is from the equation itself. X squared when the value of 1.5 x is 1.5 times 3.5 minus 10. So the answer is going to be equal to negative 2.5. And the v is equal to 1.65. So you put the values in here to get the new answer of x, it's 2.03, and y is equal to 2.8. Okay, so the most important thing is you are going to get all these values and the value of u and the value of v, and you start to put the values embed inside this equation here to get a new value of x and also the new value of y. So if you are not meet the tolerance value of error, so this means this is the new value of x minus the old value of x, and you calculate the error. If the equation is asking you the error is less than 0.5, if you not achieve, you're going to iterate one more time and so on. So this is how the method it works. This is why I told you here, you are not going to get any questions in here, because if you want to iterate with this equation, there's a lot of calculations, so you don't have that much time to do it inside the midterm or inside the final exam. So there will be no question coming from these parts, but I have to tell you how the method it works. So if you have any questions about the methods or about our class today, please ask. If not, this is the last thing for today. There is an exercise at the end of this PowerPoint slide here. Let me show it to you. There's an exercise here. It's you need to determine the roots of the following simultaneous equation using the fixed point iteration and also using the Newton-Raphson methods. Here, the initial value is given x and y. It's 1.2. And you need to iterate till the error it's less than 0.05. To solve this one using the Newton-Raphson methods, you need to iterate about at least 5 times to achieve the error less than 0.05%. So there will be a lot of calculations. So I don't think so that even you have that much time to do it for the exercise. You can just only make it for 1 iteration or 2 iteration only, and you are done with this. But try it by yourself to use it for the fixed point iteration. So that's all for our class today. If you have any questions, please ask. If not, so we consider that we finished the class. You have any questions? Is it clear?
Clear, doctor.
Okay, so before you leave in the chat box, because now you are 2 groups here, I want you to write your name and student ID in the chat box to take the attendance. Thank you very much, all. So there's a group I'm going to meet on Thursday, and there's a group I'm going to meet on Friday. See you, inshallah.
Thank you, doctor.
Take care.
Thank you.
Thank you.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.